Okay. Good morning, everyone. So thank you very much, Department of the Mathematics, GC University of Syllabus. Especially we are thankful to you, Dr. Imran Chaudhary, to organize such a great seminar on the mathematics. And we are especially thankful to you, Elisa, so joining us and giving a talk on the topic in the algebra. So I think so we have already wait 5 or 6 minutes, so we should start. And thank you very much, Elisa, once again. So let's start, please.
Hello, everyone. Thank you for having me here, and thank you to the chairperson of the Department of Mathematics, Muhammad Imran, for having me here. And today, first of all, let me share the presentation. So tell me if you can see this. Okay, can you see everybody? This one? Okay, so let me. Okay, I hope this everybody can see this. I'm very happy to be here to talk to you about what I do in my research. My name is Elisa, and I am a second-year PhD student at University of Bologna. And I work with the representations of the diagrammatic representations of the temporary Lieb algebras. So the plan for today is, first of all, to introduce some Coxeter systems and Coxeter groups, and then see how they are related to these algebras, and then we will generalize the pictures that I will show you. So first of all, a bit of history. Actually, those algebras come from statistical mechanics. And the first temporal Lieb algebra was introduced in 1971. Later, Penrose and Kaufman realized this algebra as a diagram algebra, and a diagram algebra is an algebra which is made of planar diagrams that can be multiplicated between them. On the other side, this algebra has also an abstract presentation in terms of generators and relations. And they were generalized later in 1995. And so there exists a generalized temporal Lieb algebra for each Coxeter system. So these are all words that maybe now they don't make so much sense, but let's see later what they are. So first of all, a Coxeter system. I don't know if you ever heard about them. I assure you that you already have seen them. Let me tell you why. So first of all, a Coxeter system is a pair, W and S. S is a set of generators, and W is a group, is called Coxeter group. And it has this presentation. It means that it is generated by S, the elements of S, and it has these relations. It means that we multiply S and T, which are two elements of the set S, to the power of M, ST, which is a number, a natural number. And MST is equal to MTS, and MST is equal to 1 if and only if S and T are equal. You can imagine these numbers are as the entries of a symmetric matrix with all the ones in the diagonal. So, you know, here you have the symmetry from MST equal to MTS, and you have the ones on the diagonal thanks to this other condition. Okay, so this is the presentation of the group. In a easier way, we can associate a graph called Coxeter graph to each Coxeter system. And it is made in this way. We have the nodes, we put in the elements of the set S in the nodes, and two nodes are joined with an edge if the number between S and T is equal or greater than 3. All right, so if it is equal to 2, they are not connected. If it is equal or greater than 3, they are connected. And here on the right, you have an example of a Coxeter graph. And it is the Coxeter graph of type A. So we have S1, S2, S3, Sn, which are the elements of the set S, and they are joined pairwise, S1 with S2, S2 with S3. It means that the M number between S1 and S2 is equal to 3. The M number between S2 and S3 is equal to 3, and so on. Is equal to 3 because if it was bigger than 3, we would have labeled the edge with that number. So if the edge is not labeled, it means that the M value is exactly 3. Otherwise, it is the number that we write on the edge, okay? And another thing is that S1 and S3 are not joined by an edge. It means that the M value between these two is equal to 2. All right. Here we have another 2 examples of Coxeter graphs, which are associated to the relative Coxeter systems, that is B tilde and D tilde, which are 2 examples of infinite Coxeter systems. They are divided in finite and in affine, which are the infinite one, and these 2 are 2 of the infinite ones. So, okay. These relations that are written here, the presentation, okay, let me write them more explicitly. So those relations tell us that every element of the set S is an involution, because every element to the square is equal to the identity. It also tells me that 2 elements of the set S commute, so ST is equal to TS, if the M number is equal to 2. And how do we say that? Because it is written in this row, st to the square is equal to the identity by definition. So we can write st equal to the identity. But from point 1, we know that every element is an involution. So if we multiply t to the right of both members, we cancel it from this t. So it becomes STS equal to T. We do the same thing with the S, and we obtain ST equal to TS. And this relation is called commutation relation, because I mean they commute, so commutation relation. And we have another relation which is called braid relation. And if we multiply ST as many times as the M value, it is equal to write the STS so many times as the M value. All right. If the M is equal or greater than 3. So these are the relations, and the most important are the commutation relation and braid relation. Now, here we will, so I talked to you about the general Coxeter systems. Now we will focus on the particular type A of Coxeter system. The graph is the one that you already seen in the previous slide. And let me explicit what is the Coxeter system type A. Again, we have the pair. The S, the set S is made by S1, S2, Sn, the generators that are called also reflections. So we already see that every reflection to the square is equal to the identity. In particular, they commute if their indexes are not adjacent. It means that you want to see that in the graph, they commute if the nodes are not adjacent in the graph. On the other side, they have the braid relation, which is Si, Sj, Si is equal to the reverse indexes. So Sj, Si, Sj, if the indexes are adjacent, okay, in the graph, if they are 2 nodes adjacent in the graph. And this is the type A Coxeter system. So before I told you that you have already seen that, and why? So now consider the symmetric group. I think you're familiar with the symmetric group. It is the group of all the permutations of n elements. And consider the simple transpositions I plus 1, the sigma I, which is the transposition that exchanges two numbers, two adjacent numbers, natural numbers. So if you do the computations, you can see that every simple transposition to the square is the identity. You can see that two transpositions commute if they don't have numbers in common, and that the two transpositions follow this third relation if they have one number in common. Here I give you some examples. So for example, the first one, we have the transposition 3, 4, and 6, 7, and they commute because they don't have any number in common. Otherwise, on the other hand, 1, 2, 2, 3, and 1, 2 is equal to the product 2, 3, 1, 2, 2, 3, and it is equal to 1, 3. And that's because they have one number in common. So you can do all the computations, and it is easy to verify this. And moreover, actually, the Coxeter group of type A is isomorphic to the symmetric group. And how can we show this isomorphism? By considering this map from the Coxeter group of type A to the symmetric group, which sends one generator, small reflection of the Coxeter system to the corresponding simple transposition. And you can verify it is not that difficult. You can do that as an exercise. It's quite funny actually, and you can see that actually when we talk about Coxeter system or Coxeter group of type A, we are actually talking about we are dealing with the symmetric group. So I hope so far so good. So this is just to tell you that we are actually familiar with these groups. But now I don't want to when I talk about Coxeter systems and Coxeter group, I want to express so every element of the group can be expressed as a word in the alphabet of the set S. So when we are in type A, we are not considering the simple transpositions as cycles, but we are going to write them as words, right? So S1, S2, SL, this is a word. And we say that the length of this expression is the minimum number of letters that we need to construct the word. And if this number is minimum, we call the expression reduced. We have an important result by Matsumoto, which says that, so you can imagine that for one element of the group, there is more than one reduced expression that represent this element. But the thing is, if we have two reduced expressions of one element, we can obtain one from the other only using braid or commutation relations, the one that we have seen before. So just to recall what we are talking about. So these relations, so we obtain one reduced expression from the other, just commuting generators or applying this braid relation. And that's very important, actually. It helps with all the computations. And it leads us to another definition of a subset of elements in the Coxeter group, which is the set of fully commutative elements. So an element is fully commutative if the reduced expressions can be obtained one from the other using only commutation relations. So no braid relations, only commutation relations. Here I give you an example. So let's consider it is the expression of an element in the Coxeter system of type A, A4 in particular. So let's see. We have other two expressions for this element, and how I obtained this one, the first one, I swapped S1 and S4, and then S1 and S3, you see, and then I obtain S4, S3, S1, S2, S1. But I can apply the braid relation on these three elements, S1, S2, S1. And they become S2, S1, S2, right? So since I could apply this braid relation, it tells me that this element is not fully commutative because I could apply the braid relation. When I am never able to do that, it means that we have a fully commutative element. Okay. So now let's change, let's go to another chapter and let's talk about the diagrams that will form our representation. So a diagram is a box, a rectangular box with k nodes on the top, on the north face, and k nodes on the south face. And those nodes are joined with edges. But we have rules for those. And so edges cannot cross. And every node must be the endpoint of an edge, and the edges must be embedded in the box. So in the picture, the first three are not diagrams. Just the last one, this for the fourth one, is a K diagram that we can use for our representation. And these diagrams are defined up to isotopy. What does it mean? It means that the two diagrams that you see here in the bottom of the slide are actually the same. So it doesn't matter how I deform the edges. The important thing is that they do not cross, they don't intersect. So we will consider these two diagrams equivalent up to isotopy. All right, so up to how I deform the edges. And we can also, and this is the important point, we can define a product, an associative product, in the set of the diagrams, and it will allow us to define the algebra, because the algebra is set with a very good multiplication. So we define this product by concatenation. What does it mean? We have one diagram and we put that up above another diagram, and we just obtain another diagram joining the path, joining the edges. So you see that if I join this long edge, right, you obtain this edge that connects the third node of the north face to the fifth node on the south face. Also from here, we obtain a closed loop. So in the new diagram, we have two closed loops. And if we introduce this relation, this one which is in this slide, what does it mean? It means that every time we meet a closed loop, we delete that from the diagram and we put a delta factor in front of the diagram. For example, in this picture, we delete these two. We have to delete these two loops, and we put delta to the square factor in front of the diagram. Delta to the square because there are two loops. So for each loop, we put a delta. And that allow us to define the diagram temporary Lieb algebra. So we have our main character, which is a Z delta algebra that has the diagrams that I talked to you about as basis, and with the multiplication by concatenation. And thanks to this relation, we have an algebra. So here, for example, this is the basis for the temporal Lieb algebra of type A2. The first one is the identity diagram, because if you put that above another diagram, the diagram stays the same, so we don't deform the edges. And these are all the possible way of connecting the nodes without intersections. And this is the base, and there are no closed loops because we delete them. And this is the basis for the algebra of type A2. But this algebra has this basis, right? But it has also a set of generators made of the so-called simple diagrams. Simple diagrams are very simple diagrams. That's why they are called this way. It means that they are formed by all straight lines except for the lines, for the edges that join the node I to the node I plus 1 on the north face and also in the south face. So these are very, very simple. And this is the set of generators of this diagram algebra. You can verify that these diagrams satisfy these three relations. It means that every time I multiply the one diagram with itself, one simple diagram with itself, I obtain the same diagram, but with a delta factor. Also, we can see that two diagrams commute if their indexes are not adjacent numbers, consecutive numbers. And on the other side, if the two indexes are consecutive numbers, we have this third relation. So I think now we are going to be familiar with these relations. So we saw something like this before with the Coxeter systems, but we had the first one, there was no delta factor. The second one is actually the same. The third one, it was the braid relation. Here, instead, we lose some diagram, but it will be okay, is there any question? I can see. Okay, can I go further? Okay. This is the key for constructing our representation. Here I put you the example how the relations, these three relations work. In fact, if we multiply the diagram with itself, a simple diagram with itself, you see that we obtain one loop, one closed loop, and so we have itself with a little loop, and we put a delta factor in front of that. Also, here we are multiplying two simple diagrams here in the example D1 and D3. The number are not consecutive. In fact, if we do this multiplication, we obtain this middle diagram, and we can obtain that also from multiplying these two diagrams, so D3 and D1. The last, you can see here, the last relation, we are multiplying two diagrams which indexes are consecutive numbers, and we obtain actually the first one. All right, because we go on the left and then on the right, so the edge is straight because they are equal to up to isotropy, as I said before. I hope it is clear how the multiplication works and how the simple diagrams are defined. And now this is another ingredient that then we will put everything together. And this is the abstract presentation of I think I can omit something. Okay, the abstract presentation of the temporal Lieb algebra. So the abstract definition is that this algebra is generated by the set of Bi, B2, Bn, and this set of generators satisfy these three relations. So if you look at them, at these three relations, you can see that they are exactly the same of the relations satisfied by these simple diagrams. That's why I actually built these simple diagrams in this way. So they are exactly the same relations. Another feature that I will add is that take a fully commutative element of type A. So the one that I defined above. And take a reduced expression of this S1, Si1, Sik, and consider BW the element obtained by multiplying the B generators with the same indexes of the reduced expression. All right, so that's the construction. If we consider the set of all BWs with W are all the fully commutative elements of type A, this is an important basis of this abstract algebra, and it is called monomial basis. So that's the construction, and this is all abstract. But the very important thing is this theorem, which is due to Kaufman, says that the map, if we consider this map, the map, many people are in, okay, the map from the abstract algebra to the diagram algebra that sends one generator of the abstract algebra, so one BI, to one simple diagram, the corresponding simple diagram, it is an isomorphism. So it means that these two algebras are the same. I mean, they are isomorphic. And it means that we have fully and faithfully represented the abstract algebra by our diagram algebra. They work the same, and this is what we mean with the diagrammatic representation of the temporal Lieb algebra. I hope it is clear. And it was done, I mean, in much time ago, in the 80s, no, not that much time, in the 80s and the 90s, because the temporal Lieb algebra of type A is a really classical object. And it was the one that was discovered in statistical mechanics. But as I told you, they've been generalized. So there actually exists a temporal Lieb algebra for each Coxeter system. And so the question is, can we diagrammatically represent all the other temporal Lieb algebras? Is that possible? I mean, we could do that for the classical one, type A1, type 1. Can we do that for all the other types? So the answer is almost yes. I mean, for the finite types, they were all represented, except type F, if I'm not wrong. Okay, but I mean, let's say that we're all represented. For the infinite cases, they were a little bit more complicated. And my work consisted in finding the diagrammatical representations of two types of Coxeter systems, of infinite Coxeter systems, which are B tilde and D tilde, the two Coxeter systems that I showed you in the Coxeter graphs before, maybe at the beginning. I don't know if you remember. Let me show you. So we're there. Okay, these two. So I found two representations for these two Coxeter systems, and now I want to show you the diagrams that we used for this one. So remember the diagrams that I told you about before for the classical temporal Lieb algebra. So now take them and decorate the edges. So we want to put objects on the edges, and the objects are taken in this set, the set omega of these three decorations. And we will decorate the edges with words, sequences of these elements. We have to follow rules, of course, and for example, the most important rules is this one. So it's a bit complicated. I don't know if you can see my hands, because I will explain this with my hands. Every time we have a black decoration on one edge, we have to imagine to take the edge and stretch this to the left wall of the diagram. And every time we have a white decoration, we have to imagine to take the edge and stretch this edge until the right wall of the diagram. So when we decorate a diagram, we do all these stretching moves, and we don't want that after we do the stretching moves, the edges intersect. For example, here we have two diagrams, all right? On the left, if you try to stretch the first, on the left top, we have edge decorated with a white decoration. So if you imagine to stretch that edge to the right wall, can you see that it intersects the edges that with three decorations, right? So it intersects this one. I hope you can see that I'm indicating this one. Okay. On the other side, if we do the decoration move on the right side, on the in the diagram on the right, we don't have this intersection, so we can stretch all the diagrams and no one is going to intersect with each other. So we have to follow these rules. But then other that, these are the diagrams that will form the representation. I mean, not all of them. We have to delete something. We cannot decorate as we want. And how do we do that? So you remember that before we said that every time you have a loop, you delete this and you put a delta factor in front of the diagram. Now we have 5 more relations to follow. So it was easier before because it was just one relation. Now we have 4 relations, 5 more relations. And it means that every time we put, we take 2, we have 2 consecutive white circles, they become a white triangle. Or for example, R4, it means that every time we have 2 black circles consecutive, which are consecutive, they disappear and so on. So we also consider, we can define the same multiplication as before by concatenation. So as before, we put a decorated diagram over another decorated diagram. We join the edges, all right? And then we apply the relations that you see above. So for example, in the first edge with these 3 black dots, we delete 2 dots because they disappear by R4, and then by R3 also the other dot disappears, and then you do all the computations and obtain an irreducible diagram. Irreducible because we cannot apply any other relation. So we have now these reducible diagrams. We consider a subset of these irreducible diagrams. This subset is called the set of admissible diagrams. And for example, the loops that are allowed in the admissible diagrams are only these 2 that you can see in the pictures. They have some of the restrictions, but not so many. So finally, the admissible diagrams form an algebra, and it is our diagram algebra, this time of type B tilde. And we also showed that actually this algebra is generated by the simple diagrams. And now the simple, as before, you know, as the type A algebra. And this time the simple algebra, the simple diagrams are defined as above. So they are all straight lines except the edges that connect node I to node I plus 1. But this time the first one is decorated with 2 black dots and 2 black circles, and the last one is decorated with 2 white circles. So that's the only difference. This one is the abstract presentation of the temporal Lieb algebra of type B tilde. So this time we have a couple of generators more and a couple of relations more than before. So I will not go and read this. Trust me that it is the abstract presentation of the temporal Lieb algebra of type B tilde. Again, we have the so-called monomial algebra, now considering the fully commutative element of the Coxeter system of type B tilde. So our main result was to show that this map, which is analogous to the previous one, that sends one generator of the abstract algebra to one simple diagram, this algebra is actually an isomorphism. So it means that our representation is faithful. That is our diagrammatic representation of the temporary Lieb algebra of type B tilde. And moreover, do you remember the admissible diagrams that were the diagrams that form the basis of the diagram algebra? Well, we can associate a unique to each diagram, we can associate a unique element of the monomial basis. So that basis that BW indexed by the fully commutative elements of type B. So I think I'm running out of time, so I will be very fast. Okay, I'll not talk about that, okay? And I wanted just to show you so it was the previous one was the representation type B tilde. This is the representations of type D tilde. So we use the very similar diagrams and also the results followed for the previous one. This time we have just 2 decorations. So first we have 3 decorations. Now we don't have the white circles, white triangles, sorry. We just have the white circle and the black circles. We admit another type of loop, which is this one with a circle, white circle, and everything actually is the same. So we construct the set of the admissible diagrams with those decorations, and we showed that there is an isomorphism. So we represented another algebra. So I think that's it, and thank you for your attention. If you have questions, please ask, and yeah, I hope you enjoyed my pictures.
Yes, thank you very much, Elisa, for this nice talk. I think so everybody is studying the Lieb algebra first time, but we try to gain as much more we can gain. Okay, so yes. Once again, thank you. And once again, thank you for this nice picture of the Bologna, I think so.
Yes, Bologna is actually a picture of Bologna from the PhD student's office. So
I can understand. Thank you.
Yes.
So from the audience, if you have any questions, you can ask. Okay. So Elisa, we also arrange, I think so, 10-minute talk of the undergraduate student to present the proof of the Sylow theorem. If you are happy to attend that talk, so you can attend. If you have a time.
All right.
If not, so yes. So उस्मान आप स्टार्ट करवा दें उस स्टूडेंट की टॉक अगर वो हम भी उसको अटेंड कर लें.
आप खड़ी कहाँ होंगी? ऑडियंस का बंद कर दें, कैमरा इधर इनके सामने कर दें.
Usman, you are co-host and you can share the screen and let's start. Sobia, we cannot hear you.
Invite Sobia, say please come on here and present your talk on the topic Sylow's second theorem. Sobia Saib.
No, we cannot hear you. No.
Assalamualaikum. I am Sobia from BS 7th.
Audionic, the sound master.
Assalamualaikum. I am Sobia from BS 7th morning, and today I will present Sylow's second theorem. After that, I will discuss how this theorem is pivotal. So before starting a theorem, I want to discuss some definitions like Sylow PP subgroups and conjugate subgroups and other fundamental concepts. So what is Sylow P subgroups? Sylow P subgroup is actually a subgroup whose augur is a power of prime that divides the augur of the group. Here are some examples. For example, symmetric group, we have 3 Sylow 2 subgroups of augur 2 and 1 Sylow 3 subgroups of augur 3. Now, similar to the relation of conjugacy between elements of a group, we have conjugacy relation between the subgroups of a group. So, that is 2 subgroups H and K are said to be conjugate subgroups if there exists an element X from G such that H is equal to X, K, X inverse. Now, if we define a relation on group as 2 elements of the group A and B are related, if and only if there exists an element H from a subgroup H and K from a subgroup K, such that A equals to BH, BKH, then we can easily see that this relation is an equivalence relation. So it will divide the group into the disjoint union of equivalence classes. And these equivalence classes are nothing but are double cosects. I have mentioned here double cosects. Now, if we define a function from a double cosect hx k from hx k to the internal product of h and x qx inverse, then we can see that we can find the order of equivalence class, that is double cosect xp x inverse. So now we are ready to prove Sylow's second theorem. We prove this theorem by contradiction. This theorem states that any two Sylow P subgroups, are conjugate in G. We prove this by contradiction. So we take any two Sylow P subgroups and we suppose that they are not conjugate in G. That is P is not equals to G, Q, G inverse for any G belongs to group. Now we have discussed that the order of the equivalence class PXQ is equal to order of P into order of Q over order of P intersection XQ X inverse. And here we know that P and XQ X inverse are two subgroups. So their intersection will be a subgroup again. And by Lagrange's theorem, we know that the order of the subgroup divides the order of the group. So here the order of P intersection XQ X inverse, which is a subgroup of G, has order P raised to power MC, the divisor of the order of the group, where M is less than equals to N. Now we have two possibilities. If we take M equal N, then we see that we have a contradiction, because here we have P equals to XQ X inverse, but we have supposed that P and Q are not conjugate. So here we find that X such that P equals to XQ X inverse, which shows that P and Q are conjugate, but we have supposed that P and Q are not conjugate. So it means that M is less than N. And from the order of the equivalence class, we find that order of PXQ equals to P raised to power 2N minus P. And simplifying this, we find that order of PXQ is actually a multiple of P raised to power N plus 1. We know that PXQ is actually an equivalence class. So if the order of PXQ is a multiple of P raised to power N plus 1, so is the order of the group. That is, the order of the group will also be the multiple of P raised to power N plus 1. But we have supposed that the order of the group is not the multiple of P raised to power N plus 1. That is, P raised to power N plus 1 does not divide the order of the group. It means that we have a contradiction again. And this means that any two Sylow P subgroups are actually conjugate in G. Now, what if we want to determine whether two conjugate subgroups are isomorphic instead? The answer is very simple. We know that any two conjugate subgroups of a group are isomorphic. This means that by using Sylow's second theorem, we conclude that any two Sylow P subgroups are also isomorphic. Here is an example application in S3. In S3, we can see that the other application here is by knowing one Sylow P subgroup, we can find all the other Sylow P subgroups of a group. Because if we know one Sylow P subgroup, we can find the conjugacy class of that Sylow P subgroup. And we know that by Sylow's second theorem that any two Sylow P subgroups are conjugate, Therefore, conjugacy class will give all the Sylow P subgroups of a group. So it means that from Sylow's second theorem, we can find that any two Sylow P subgroups are conjugate, and this will further imply that any two Sylow P subgroups are isomorphic. And if we have only one Sylow P subgroup, we can find all the other by conjugation. This is all about my presentation. Any question?
Any question from the audience?
Elisa, do you have any question? Elisa.
No, I don't. Thank you.
Okay. So, Sobia, thank you very much for your talk. I have maybe very yes. Yes. Mohsen, can you hear me? Hello.
Hello, Mr. Jawad, can you hear my voice?
Yes. Okay, I have some questions. Can you hear me, Sobia?
Yes.
Sobia, you are using a finite group in your like statement of the theorem? Why you are not using the in general group? Why you are not using the infinite group?
We have used here finite groups because in the Sylow second theorem, we have mentioned Sylow P subgroups. And in the definition of Sylow P subgroups, we have only finite groups under discussion. So we can take infinite groups. We can take because in Sylow P subgroups, if we have an infinite group, then in this case, we can find any prime divisor. Actually, we are discussing finite group theory because we only want to know order of the group. So that's why we only take finite groups.
Okay, thank you. And other question is that you are using isomorphic. What is the actual meaning of the isomorphic between the two sets?
Isomorphism is actually if we have two sets are isomorphic, then it means that by knowing one set, we can by knowing one set and its or the important properties, we can find all the important elements, properties of the other set. If we discuss only one set, then this is equivalent that we discuss all the sets that are isomorphic to that set.
If we have a two set, like we have a set A and we have a set B, the map between
Yes.
set A and B is isomorphic. So
Yes.
what does it mean? What things are preserved under this map? Do you know?
If we have two set and
Yes, and a map from A to B is isomorphic. Do you know what things are the preserved under this map?
under this map group, all the operations are preserved. For example, if we have an isomorphism between two groups, then the operation of the groups are preserved by this isomorphism, because isomorphism is actually bijective homomorphism.
Okay.
Operation
So
preserving map actually.
thank you very much, Sobia. It's a nice talk. And thank you once again. Thank you, Math Outreach Society, to organize this nice talk. And in the last, Sobia gave the nice proof of the Sylow second theorem. So see you once again in the next time. Thank you, Usman. Thank you, Mohsen. And once again, thank you, Sarimran, to organize this such a great talk.
Thank you so much.
Bye.
Bye. Thank you.
Bye. Thank you.